non-man-made energy inputs. The natural or primary energy sources are not usually included in the calculation of energy invested, only the human-applied sources. For example, in the case of biofuels, the solar insolation driving photosynthesis is not included, and the energy used in the stellar synthesis of fissile elements is not included for nuclear fission. The energy returned includes usable energy and not waste such as heat, although depending on source and application, waste heat is used in district heating and water desalination. These cogeneration plants, however, are rare globally, and thus usually excluded in Eroei analysis of energy sources. Low-carbon power. A 2015 review in Renewable and Sustainable Energy Reviews assessed the energy payback time and ROI of solar photovoltaics. In this study, which uses an insolation of 1700 kWh per square meter year and a system lifetime of 30 years, mean harmonized ROIs between 8.7 and 34.2 were found. Mean harmonized energy payback time varied from 1.0 to 4.1 years. A review Picard reports Eroei estimates for monocrystalline silicon photovoltaics by 4 groups in the range of 2.2 to 8.8. It should be noted that Eroei is a function of the solar irradiation level and the type of PV technology. It also depends on methodology and system boundary assumptions. Rauge, Fulana I. Palmer and F. The Narkis show Eroei in the range of 5.9 to 11.8 and 19 to 39 for the major commercial PV types in South European installations. The low range assumes that primary energy and electricity are of the same quality, whereas the high range is calculated by converting the electricity output of PV to primary energy as recommended by the IEA PVPS-12 LCA methodology guidelines. Furthermore, F. The Narkis determined the Eroei to be as high as 60 for the least energy-consuming thin-film PV technology installations in the U.S. Southwest. The Eroei of wind turbines depends on invested energy in the turbine, produced energy and lifespan of a turbine. In the scientific literature, Eroeis normally vary between 20 and 50. Economic influence of Eroei. High per capita energy use has been considered desirable as it is associated with a high standard of living based on energy-intensive machines. A society will generally exploit the highest available Eroei energy sources first, as these provide the most energy for the least effort. This is an example of David Ricardo's best first principle. Then progressively lower quality or ZOR energy resources are used as the higher quality ones are either exhausted or in use. For example, wind turbines positioned in the windiest areas. In regard to fossil fuels, when oil was originally discovered, it took on average 1 barrel of oil to find, extract, and process about 100 barrels of oil. The ratio for discovery of fossil fuels in the United States has declined steadily over the last century from about 1,000 to 1 in 1919 to only 5 to 1 in the 2010s, although many qualities of an energy source matter. When the Eroei of the main sources of energy for an economy fall, that energy becomes more difficult to obtain and its relative price increases. Therefore, the Eroei gains importance when comparing energy alternatives, since expenditure of energy to obtain energy requires productive effort. As the Eroei falls, an increasing proportion of the economy has to be devoted to obtaining the same amount of net get energy. Since the invention of agriculture, humans have increasingly used exogenous sources of energy to multiply human muscle power. Some historians have attributed this largely to more easily exploited energy sources, which is related to the concept of energy slaves. Thomas Homer Dixon argues that a falling Eroei in the later Roman Empire was one of the reasons for the collapse of the Western Empire in the 5th century CE. In The Upside of Down, he suggests that Eroei analysis provides a basis for the analysis of the rise and fall of civilizations, looking at the maximum extent of the Roman Empire and its technological base. The agrarian base of Rome was about 112 per hectare for wheat and 127 for alfalfa. One can then use this to calculate the population of the Roman Empire required at its height, on the basis of about 2,500 minus 3,000 calories per day per person. It comes out roughly equal to the area of food production at its height. But ecological damage saw a collapse in the system beginning in the 2nd century, as Eroei began to fall. It bottomed in 1084 when Rome's population, which had peaked under Trajan at 1.5 million, was only 15,000. Evidence also fits the cycle of Mayan and Cambodian collapse too. Joseph Tainter suggests that diminishing returns of the Eroei is a chief cause of the collapse of complex societies. This has been suggested as caused by peakwood in early societies. Falling Eroei due to depletion of high-quality fossil fuel resources also poses a difficult challenge for industrial economies. Tim Garrett links Eroei and inflation directly, based on a thermodynamic analysis of historical world energy consumption and accumulated global wealth. This economic growth model indicates that global Eroei is the inverse of global inflation over a given time interval. Because the model aggregates supply chains globally, local Eroei is outside its scope. Oil sands. Because much of the energy required for producing oil from oil sands comes from low-value fractions separated out by the upgrading process, there are two ways to calculate Eroei. The higher value given by considering only the external energy inputs, and the lower by considering all energy inputs including self-generated. See oil sands #input energy. Utilize detailed energy production and consumption data reported by oil sands producers from 1970 to 2010 to examine trends in historical energy returns from oil sands extraction. Quote, they argued that by 2010, NERs from oil sands mining and in-situ operations had become significantly more energy efficient since 1970, although the NER remained significantly less efficient than conventional oil production. NERs from the oil sands grew from 1.0 gigajoules GJ in 1970 to 2.95 gigajoules GJ in 1990, and then to 5.23 gigajoules GJ in 2010. Criticism of Eroei. Measuring the Eroei of a single physical process is unambiguous, but there is no agreed-upon standard on which activities should be included in measuring the Eroei of an economic process. In addition, the form of energy of the input can be completely different from the output. For example, energy in the form of coal could be used in the production of ethanol. This might have an Eroei of less than 1, but could still be desirable due to the benefits of liquid fuels. How deep should the probing in the supply chain of the tools being used to generate energy go? For example, if steel is being used to drill for oil or construct a nuclear power plant, should the energy input of the steel be taken into account? Should Should the energy input into building the factory being used to construct the steel be taken into account and amortized? Should the energy input of the roads which are used to ferry the goods be taken into account? What about the energy used to cook the steel workers' breakfasts? These are complex questions evading simple answers. A full accounting would require considerations of opportunity costs and comparing total energy expenditures in the presence and absence of this economic activity. However, when comparing two energy sources, a standard practice for the supply chain energy input can be adopted. For example, consider the steel, but don't consider the energy invested in factories deeper than the first level in the supply chain. Energy return on energy invested does not take into account the factor of time. Energy invested in creating a solar panel may have consumed energy from a high-power source like coal, but the return happens very slowly, i.e. over many years. If energy is increasing in relative value, this should favor delayed returns. Some believe this means the Eroei measure should be refined further. Conventional economic analysis has no formal accounting rules for the consideration of waste products that are created in the production of the ultimate output. For example, differing economic and energy values placed on the waste products generated in the production of ethanol makes the calculation of this fuel's true Eroei extremely difficult. Eroei is only one consideration and may not be the most important one in energy policy. Energy independence, decrease of greenhouse gas emissions, and affordability could be more important, particularly when considering secondary energy sources. While a nation's primary energy source is not sustainable unless it has a use rate less than or equal to its replacement rate, the same is not true for secondary energy supplies. Some of the energy surplus from the primary energy source can be used to create the fuel for secondary energy sources, such as for transportation. Richards and Watt propose an energy yield ratio for photovoltaic systems as an alternative to Eroei. The difference is that it uses the design lifetime of the system, which is known in advance, rather than the actual lifetime. This also means that it can be adapted to multi-component systems where the components have different lifetimes. Another issue with Eroei that many studies attempt to tackle is that the energy return can be in different forms, and these forms can have different utility. For example, electricity can be converted more efficiently than thermal energy into motion due to electricity's lower entropy. Additional Eroei calculations. There are three prominent expanded Eroei calculations. They are point of use, extended and societal. Point of use Eroei expands the calculation to include the cost of refining and transporting the fuel during the refining process. Since this expands the bounds of the calculation to include more production process, Eroei will decrease. Extended Eroei includes point of use expansions as well as including the cost of creating the infrastructure needed for transportation of the energy or fuel once refined. Societal Eroei is a sum of all the Eroeis of all the fuels used in a society and nation. A societal Eroei has never been calculated, and researchers believe it may currently be impossible to know all variables necessarily to complete the calculation, but attempted estimates have been made for some nations. Calculations done by summing all of the Eroeis for domestically produced and imported fuels and comparing the result to the Human Development Index, a tool often used to understand well-being in a society. According to this calculation, the amount of energy a society has available to them increases the quality of life for the people living in that country, and countries with less energy available also have a harder time satisfying citizens' basic needs. This is to say that societal Eroei and overall quality of life are very closely linked. ESOEI is used when EROEI is below 1. EROEI under rapid growth. A related recent concern is energy cannibalism, where energy technologies can have a limited growth rate if climate neutrality is demanded. Many energy technologies are capable of replacing significant volumes of fossil fuels and concomitant greenhouse gas emissions. Unfortunately, neither the enormous scale of the current fossil fuel energy system nor the necessary growth rate of these technologies is well understood within the limits imposed by the net energy produced for a growing industry. This technical limitation is known as energy cannibalism and refers to an effect where rapid growth of an entire energy-producing or energy efficiency industry creates a need for energy that uses the energy of existing power plants or production plants. The solar breeder overcomes some of these problems. A solar breeder is a photovoltaic panel manufacturing plant which can be made energy independent by using energy derived from its own roof using its own panels. Such a plant becomes not only energy self-sufficient but a major supplier of new energy, hence the name solar breeder. Research on the concept was conducted by Centre for Photovoltaic Engineering, University of New South Wales, Australia. The reported investigation establishes certain mathematical relationships for the solar breeder which clearly indicate that a vast amount of net energy is available from such a plant for the indefinite future. The solar module processing plant at Frederick, Maryland was originally planned as such a solar breeder. In 2009, the Sahara solar breeder project was proposed by the Science Council of Japan as a cooperation between Japan and Algeria with the highly ambitious goal of creating hundreds of GW of capacity within 30 years. Theoretically, breeders of any kind can be developed. In practice, nuclear breeder reactors are the only large-scale breeders that have been constructed as of 2014, with the 600 MW EBN 600 and 800 MW EBN 800 reactor, the two largest in operation.